Let me ask you a question. Imagine I place a cat inside a sealed box. Inside that same box, there's a tiny radioactive atom. If the atom decays, it triggers a mechanism that releases poison, and the cat dies. If the atom doesn't decay, the cat lives. Now here's the strange part. Before you open the box, is the cat alive or dead? Your common sense says it has to be one or the other. But according to one of the strangest ideas in quantum physics, the cat is both alive and dead at the same time, until someone looks. Sounds ridiculous, doesn't it? Good, because that's exactly why this thought experiment became one of the most famous ideas in science. Today, we're not just talking about a cat in a box. We're exploring a question that challenges reality itself. Does the universe have a definite state before we observe it? By the end of this talk, you'll understand Schrödinger's cat in the simplest way possible, and you'll never think about reality the same way again. Have you ever noticed something fascinating about the way we think? We assume that everything around us has a definite answer. If I ask whether the lights in this room are on or off, you expect one clear answer. If I ask whether your front door is open or closed, again, it's one or the other. Our brains are trained from childhood to believe that reality is always settled, whether we're looking at it or not. That's how the everyday world works. It's predictable. It's comfortable. It makes sense. But what if I told you that nature, at its smallest scale, doesn't always follow the rules that our common sense depends on? Imagine I bring a small wooden box onto this stage. It's completely sealed. You can't see inside it, I can't see inside it, and no one in this room has any idea what's happening within it. Inside that box is a perfectly healthy cat. The cat has food, air, and everything it needs. Nothing unusual so far. Now imagine there's something else inside the box, a tiny piece of radioactive material. Radioactive atoms behave in a very strange way. Scientists can calculate the probability that an atom will decay over a certain period of time, but no one, not the smartest physicist, not the most advanced computer, not even the laws of physics themselves, can predict the exact moment when a single atom will decay. It might happen in the next second. It might happen an hour from now. Or it might not happen at all during the entire experiment. That's already a little unsettling. We're used to believing that if we know enough information, we should be able to predict everything. But quantum mechanics tells us something different. At the microscopic level, nature is built on probabilities rather than certainty. Now let's connect that tiny atom to something much larger. Suppose that if the atom decays, it activates a detector. The detector immediately breaks a small glass vial containing poison gas. The poison fills the box, and sadly, the cat dies. But if the atom doesn't decay, nothing happens. The poison remains sealed, and the cat stays alive, completely unaware that it's part of one of the most famous thought experiments ever imagined. Now, I want you to stop for a moment and answer this question in your own mind. The box has been closed for exactly 1 hour. Nobody has opened it. Nobody has looked inside. What is the condition of the cat? Most people immediately answer, well, either it's alive or it's dead. We just don't know which one yet. That sounds perfectly reasonable, because that's how we experience the world every day. If I flip a coin and cover it with my hand, the coin doesn't wait for me to look before deciding whether it's heads or tails. The result already exists. My ignorance doesn't change reality. But according to the strange mathematical rules of quantum mechanics, something astonishing seems to happen. Before the box is opened, the radioactive atom isn't simply undecided because we lack information. Instead, it exists in what physicists call a superposition, a combination of multiple possible states described by the mathematics of quantum theory. And because the fate of the cat depends entirely on that atom, the mathematics suggests something deeply disturbing. Before anyone opens the box, the cat is described as being both alive and dead at the same time. Not because the cat is magically switching back and forth, but because the quantum system itself contains both possibilities simultaneously. The first time people hear this idea, they usually laugh. They think it's a joke or a trick. Some people even assume physicists have lost their minds. But here's the fascinating part. This wasn't invented because scientists believed cats could literally be alive and dead at once. In fact, the scientist who created this thought experiment, Erwin Schrödinger, wanted to show just how bizarre quantum mechanics sounded when you applied it to everyday objects. He was saying, look how strange this becomes. If the equations are taken literally, then even something as ordinary as a cat seems to end up in two completely different states until someone looks. That's what made this thought experiment unforgettable. It takes an invisible quantum event, something happening inside a single atom, and stretches it into a situation that every human being can picture. Suddenly, an abstract mathematical idea becomes an emotional story. Nobody wants to imagine a cat trapped inside a mysterious box. And because the image is so vivid, it forces us to confront a much bigger question. Does reality exist in one definite form before it's observed? Or does the universe behave in ways that are completely different from anything our everyday experience has prepared us to understand? That simple imaginary box, containing nothing more than a cat, a tiny atom, and a little bit of poison, became one of the greatest symbols of modern physics. It reminds us that the universe isn't obligated to match our intuition. Sometimes, the deeper we investigate reality, the stranger it becomes. And perhaps the most incredible part of all is that this isn't science fiction. It grew out of one of the most successful scientific theories ever developed, a theory that accurately predicts the behavior of the microscopic world with astonishing precision, even if its meaning continues to puzzle scientists to this day. Now, if that story about the cat sounded strange, I have to warn you. The really strange part hasn't even begun yet. The cat was only a way to help us picture something much smaller, something happening in the invisible world of atoms and electrons. To understand why physicists even imagined a cat being both alive and dead, we first have to understand one of the most extraordinary ideas ever discovered in science: quantum superposition. The word superposition sounds technical, but the idea behind it is surprisingly simple if we approach it step by step. Think about a light switch in your house. It can only be in one of two positions. It's either on or off. There isn't a third option where it's somehow both at the same time. The same is true for a coin. When you flip it, it eventually lands as either heads or tails. Even if you cover the coin before looking at it, the result has already been decided. You simply don't know what it is yet. That's how every object in our daily lives behaves. We call this common sense because it has worked for every experience we've ever had. But when scientists began studying nature at incredibly small scales, something remarkable happened. Electrons, photons, and other tiny particles refused to follow these familiar rules. Every experiment seemed to reveal the same shocking conclusion. Before a measurement is made, these particles don't appear to occupy just one definite state. Instead, they behave as though multiple possible states exist together in a single mathematical description. That sounds impossible because our brains naturally picture objects as little solid things moving through space, almost like microscopic marbles. But quantum particles don't behave like tiny marbles. They behave according to the strange mathematics of quantum mechanics, and those equations consistently describe a particle as existing in a combination of possibilities until an interaction occurs. Imagine you're standing at the entrance of a maze. Normally, if you wanted to reach the exit, you would choose one path, walk along it, and eventually discover whether it was the correct route. That's how we think movement should work. But imagine a magical traveler who somehow explores every possible path through the maze at the same time. Instead of committing to one route, every possible route is explored simultaneously. Then, when the journey ends, only one outcome becomes visible. That isn't exactly what a quantum particle does, but it's much closer to reality than imagining it as an ordinary tiny ball following one fixed path. Here's another way to think about it. Suppose you're listening to an orchestra. Before the conductor begins, every musician is holding their instrument, ready to play. The music exists only as possibilities. There are countless melodies that could fill the concert hall, but none has yet become the actual performance. Once the conductor raises the baton and the orchestra begins, one particular arrangement of notes becomes reality. Quantum systems are different, of course, but the comparison reminds us that possibility can sometimes be just as important as certainty. One of the greatest challenges in understanding quantum mechanics is that our language evolved to describe everyday experiences, not the microscopic world. Words like here, there, moving, waiting, and existing carry assumptions that work perfectly for cars, trees, people, and planets. But atoms don't always obey those assumptions. When physicists say a particle exists in a superposition, they aren't saying the particle is confused. They aren't saying nature can't make up its mind. They aren't saying the particle rapidly jumps back and forth between different states. Instead, they're describing a mathematical reality that successfully predicts experimental results with astonishing accuracy, even though it challenges our intuition. This is why quantum mechanics feels so uncomfortable. It asks us to separate what feels obvious from what experiments actually reveal. Consider sunlight for a moment. Every second, trillions of tiny particles of light, called photons, stream toward Earth. If light behaved exactly as we expected, every photon would simply travel like a tiny bullet from the sun to your eyes. But countless experiments have shown something much stranger. Light sometimes behaves like a particle. At other times, it behaves like a wave. Even more astonishing, individual particles can produce wave-like interference patterns that seem to imply they explored multiple possibilities before arriving at a final result. Scientists didn't invent these ideas because they sounded exciting. In fact, they resisted them for years because they seemed absurd. They accepted them because experiment after experiment left no alternative. Nature kept giving the same answer, even when that answer contradicted human intuition. Now let's return to our cat. The cat itself is not a quantum object in the way an electron is. Cats are enormous compared to atoms. They interact constantly with their environment. They breathe, move, exchange heat with the air, and are influenced by countless microscopic events every second. In everyday life, we never observe cats wandering around in quantum superposition. So why use a cat at all? Because Schrödinger wanted to expose the uncomfortable bridge between the microscopic and the macroscopic worlds. If a tiny radioactive atom can exist in a superposition, and that atom directly controls a deadly mechanism, then doesn't the entire system, including the cat, become linked to those same possibilities? That question shook the scientific community because it wasn't just about cats. It was about reality itself. Where does the strange quantum world end and the familiar everyday world begin? Is there a hidden boundary somewhere between atoms and living creatures? Or are the same quantum rules operating everywhere, with larger objects simply becoming too complex for us to notice? These questions remain some of the deepest mysteries in modern physics. Perhaps the most beautiful lesson hidden inside the idea of superposition is that nature doesn't owe us simplicity. For centuries, humanity believed the universe should behave in ways that matched common sense. Then science repeatedly humbled us. The Earth wasn't the center of the universe. Time wasn't absolute. Space itself could bend. And now quantum mechanics tells us that certainty may not be as fundamental as we once believed. The more deeply we investigate reality, the more we discover that the universe is not stranger than we imagined. It is stranger than we were prepared to imagine. Superposition is one of the clearest reminders that our intuition was shaped for survival on the African savanna, not for understanding the invisible machinery of the quantum world. Yet through mathematics, careful experiments, and relentless curiosity, we have managed to glimpse a reality far more mysterious and beautiful than anyone could have predicted. Now we've reached the question that has puzzled scientists, philosophers, and some of the greatest minds in history for nearly a century. We've imagined the sealed box. We've followed the radioactive atom. We've accepted, at least for the sake of discussion, that quantum mechanics describes the atom as existing in a superposition of possibilities. But now comes the question that changes everything. What actually happens when someone opens the box? It sounds like such an ordinary action. You simply lift the lid and look inside. That's all. We do things like this every day without giving them a second thought. We open a refrigerator. We open a book. We open a door. Looking seems passive. It feels as though we're merely discovering something that was already there. But quantum mechanics forces us to ask whether observation is really that simple. Imagine you're the person standing in front of the box. An entire hour has passed. Everyone in the room is silent. Every eye is fixed on your hands. You slowly reach forward. Your fingers touch the lid. Your heart begins to race because you know that inside the box there is only one of two possible outcomes. The cat is alive or the cat is dead. As you lift the lid, one reality immediately confronts you. Perhaps the cat is stretching peacefully, completely unharmed, or perhaps the poison was released long ago. Either way, the moment you look, there is no uncertainty anymore. There is only one outcome. This is where many people make an understandable mistake. They think the mystery is simply about learning information. They assume that opening the box is no different from uncovering a hidden playing card or revealing the answer to a quiz. But quantum mechanics suggests something far stranger. The mathematical description of the system changes when a measurement occurs. Before measurement, multiple possible outcomes are represented in the quantum state. After measurement, we observe only one definite result. This transition has become one of the most debated ideas in all of science. What exactly counts as a measurement? What qualifies as an observation? Where does one possibility disappear while another becomes the reality we experience? Those questions are far more difficult than they first appear. Many people hear the phrase observation changes reality and immediately imagine that human consciousness possesses mysterious powers, that simply looking with your eyes somehow forces the universe to make a decision. That's a popular idea in movies, television shows, and internet discussions. But the actual science is much more subtle. In quantum physics, a measurement does not necessarily require a conscious human being. A quantum system can interact with a detector, another particle, or its surrounding environment. These interactions can be enough to destroy the delicate quantum superposition, a process that physicists often describe through the idea of decoherence. The mathematics shows that once a quantum system becomes strongly entangled with its environment, the clean superposition rapidly becomes inaccessible in the way it existed before. So the real mystery isn't that human eyes possess magical abilities. The mystery is understanding why the elegant quantum description of many possibilities gives rise to the single definite reality that every one of us experiences. This is sometimes called the measurement problem, and despite decades of research, there is still no universal agreement about its ultimate solution. Different physicists have proposed different interpretations. Some argue that the quantum wave function simply collapses during measurement. Before observation, multiple possibilities exist mathematically. During measurement, one possibility becomes the observed reality. Others disagree entirely. According to the many worlds interpretation, the wave function never collapses at all. Instead, every possible outcome actually occurs, but in different branches of the universe. In one branch, the cat lives. In another branch, the cat dies. Each observer experiences only one branch, giving the impression that only a single outcome exists. Imagine how astonishing that idea is. Every quantum event would continually divide reality into countless branching histories. Somewhere, according to this interpretation, every possible quantum outcome unfolds. Whether that picture reflects reality remains an open question, but it demonstrates just how extraordinary the consequences of quantum theory can become. Other physicists believe there are hidden variables, unknown pieces of information that we simply haven't discovered yet. They argue that beneath the apparent randomness, nature may still possess deeper rules waiting to be uncovered. Still others suggest that our current understanding is incomplete and that an entirely new theory may eventually replace or extend quantum mechanics. Notice something remarkable about this situation. These scientists are not arguing because the experiments disagree. The experiments overwhelmingly support the predictions of quantum mechanics. The mathematics works with extraordinary precision. Technologies like lasers, semiconductors, MRI machines, and quantum computers all rely on these principles. The disagreement is about what the mathematics actually means. Think about how unusual that is. Normally in science, once experiments agree with a theory, the interpretation becomes obvious. Here, the predictions are among the most accurate ever achieved, yet the deeper meaning remains one of the greatest unsolved questions in physics. Richard Feynman once expressed this beautifully when he suggested that if someone believes they truly understand quantum mechanics, they probably don't understand it in the way they think they do. That wasn't a criticism of the theory. It was a recognition that quantum reality refuses to fit comfortably inside everyday intuition. And perhaps that's exactly why Schrödinger's cat continues to fascinate people decades after it was first imagined. It isn't really about a cat. It isn't even about a box. It's about the limits of human understanding. Every generation of scientists has inherited the same mystery. They design more precise experiments, build more powerful computers, develop more elegant mathematics, and continue pushing deeper into the quantum world. Each discovery answers old questions while opening entirely new ones. The universe keeps reminding us that reality is not obligated to match our expectations. When we were children, we believed the world was simple because it appeared simple. Then science gradually revealed invisible atoms, curved space-time, black holes, dark matter, and the strange quantum behavior of particles, each discovery carried the same lesson. Reality is always richer than appearances. So when you think back to Schrödinger's cat, don't picture it merely as a clever story from a physics textbook. Picture it as a doorway into one of the deepest questions humanity has ever asked. Does reality exist in a definite form before it is measured? Why do countless quantum possibilities give rise to the single world we experience? Will future generations finally discover the answer, or is the mystery itself part of the fabric of nature? We don't yet know. And that may be the most inspiring part of all. Science is not a collection of final answers. It is an endless journey of better questions. Schrödinger's cat reminds us that even after nearly 100 years of astonishing progress, the universe still holds secrets capable of surprising the brightest minds on Earth. The more honestly we investigate reality, the more we discover that certainty is rare, curiosity is essential, and the greatest discoveries often begin with the courage to ask a question that sounds completely impossible. The goal today isn't just to explain a famous physics experiment. It's to show you that the universe is far stranger and far more fascinating than our everyday experience suggests. Once you understand Schrödinger's cat, you'll begin to see why quantum mechanics continues to amaze even the world's greatest physicists.